All right, let's dive right into the fascinating cat and mouse game of internet security. You know that little padlock next to your URL? Well, welcome to this explainer. Today, we're uncovering the invisible infrastructure that puts it there, keeping your data safe every single time you browse the web. Because really, what is actually happening behind the scenes to guarantee that security?
In this explainer, we're going to break this down step by step. Number 1, the internet's trust problem. 2, enter certificate authorities. 3, proving your web identity. 4, when certificates fail. And finally, 5, the revocation dilemma. So let's get into it.
Starting with Section 1, the Internet's trust problem. To really grasp the brilliant solution that secures the modern web, we first need to understand the terrifying vulnerability we're actually trying to fix.
Imagine you're trying to securely connect to google.com. When you connect to a server, it hands you a public key to encrypt your data. But here is the massive problem. What if an attacker is sitting right in the middle of your connection, intercepting your request and handing you their public key instead? If you use their key, that attacker can decrypt, read, and manipulate everything you send. So how does your browser actually know for sure it's talking to the real Google?
Now, there's a pretty fascinating contrast in how different systems try to solve this whole mess. Take systems like SSH, for example. They use a model called TOFU, trust on first use. With TOFU, your computer just remembers the very first key it ever sees from a server. That's great, it's incredibly simple, and it doesn't require any third parties. But it has a fatal flaw. If you are attacked by a man in the middle on your very first connection, you are going to trust that attacker's key forever. And that is exactly why the wider public web needed something far more robust, the certificate authority model. Which brings us to Section 2, enter certificate authorities. To fix those massive flaws with trust on first use, the web had to bring in a powerful middleman. We call these middlemen certificate authorities, or CAs for short. You can kind of think of them like a digital passport agency. A CA takes a specific domain name, like google.com, and a specific public key, and binds them tightly together using their own secret signing key. This creates a digital certificate. So when a server hands you the certificate, your browser can just check the CA signature to verify that, yep, this public key officially belongs to this domain name. But wait a second, how do you know you can actually trust the CA's signature in the first place? It's a total chicken and egg problem, right? Well, the answer is literally baked right into your computer. Browsers like Google Chrome come pre-installed from the factory with a hard-coded list of around 100 trusted certificate authority root keys. If you bought a new laptop or just downloaded Chrome, those 100 public keys came right along with it, forming the absolute foundation of your web trust. Moving right along to Section 3, proving your web identity. Okay, so we know CAs issue these digital passports, but this raises a huge question. How does a server actually prove to the CA that it truly owns the domain name it's asking a certificate for?
This is where a standard called the ACME protocol comes into play. When a server wants a certificate from a modern CA, like Let's Encrypt, the CA essentially issues a challenge. It generates a totally random string of numbers and letters called a nonce and tells the server, okay, if you really own this website, post this exact random puzzle piece on your webpage. The CA then goes to that URL. If it sees the puzzle piece displayed, it knows for a fact the server controls the domain and boom, it hands over the certificate. But, attackers are clever. What if a bad actor is just sitting on your local network and intercepts the CA's challenge request? Well, to prevent a local network attacker from faking the response, the CA brilliantly uses multi-perspective validation. It doesn't just check your website from one computer. It checks for that puzzle piece from 5 different validator locations across the globe, simultaneously. An attacker would literally have to compromise the internet's routing on a global scale to fake that. All right, Section 4, when certificates fail. Because as bulletproof as all of that sounds, absolutely no system is perfect. Let's look at the blind spots in this invisible infrastructure.
Certificates do exactly what they were designed to do, but they definitely have limits. First off, they can't stop you from being tricked by lookalike phishing domains. I mean, if you go to Amazon.com, but with a 0 instead of an O, the CA is still going to happily issue a valid certificate for that fake site, and your browser will show that secure padlock. Second, they can't always stop attackers from blocking the secure connection entirely and forcing your browser to downgrade to an unencrypted HTTP connection. And third, they just fail completely when there's a disconnect between your intent and the domain name. Like when you connect to a university Wi-Fi network, say MIT, you aren't actually typing in a specific domain name. Your computer doesn't know what certificate to expect, so it blindly falls back to that super vulnerable trust on first use model we talked about earlier.
Now, because CAs themselves can be tricked or compromised or honestly just make dumb mistakes, the industry had to build a safety net. Enter certificate transparency logs, or CT logs. Think of these like a giant digital town square bulletin board. Every single time a CA issues a certificate, it is legally required to pin a copy of it to this public, completely unalterable ledger.
And this brilliantly illustrates the whole philosophy here. Even if a client gets tricked with a bad certificate, at least someone out there knows. We might not be able to prevent every single bad certificate from being issued in the first place, but CT logs guarantee that attackers absolutely cannot do it in secret. Website owners can constantly monitor these public logs. So, if a fake certificate for your website suddenly pops up on the ledger, you can instantly sound the alarm and get it revoked.
Which leads us to Section 5, the revocation dilemma. We've arrived at the absolute messiest, most highly debated part of web security, cleaning up after a disaster.
Think about it like this. Let's say a certificate is good for a whole year. What happens if a hacker breaks into the web server and steals the private key on day 2? The certificate itself is still technically valid for another 363 days. The attacker can perfectly impersonate the website, intercepting and decrypting traffic until that certificate is actively and aggressively revoked.
And the industry has literally gone in circles for decades trying to fix this revocation dilemma. Back in the 90s, they just relied on long expiration dates. Then, in the 2000s, they introduced CRLs, these massive, ridiculously slow lists of revoked keys that browsers had to download. It took forever. To fix that, they tried OCSP, which were basically live checks to the CA every single time you visited a site. But, as you might guess, that totally ruined user privacy because the CA suddenly knew every single website you visited. Then they tried OCSP stapling, where the server itself fetches the proof of validity. It's just been this constant, agonizing tug of war between security, speed, and privacy. Ultimately, all those older revocation systems were so incredibly clunky and flawed that the modern solution is surprisingly simple. Abandon complex revocation entirely and just shrink the certificate lifespans. We've moved from certificates that lasted years down to just 90 days. And because protocols like Acme have automated the entire renewal process, the industry's plan is to drop lifespans to a mere 7 days in the very near future. If a key is stolen, the attacker only has a few days to use it before the certificate just naturally dies. Which leaves us with a pretty fascinating final thought to wrap up this explainer. If automated systems are constantly refreshing the web security logs every few days just to keep us safe behind the scenes, it makes you wonder about our own security. What invisible cryptographic safety nets are going to entirely replace passwords for us next? The underlying cryptography here is evolving incredibly fast, paving the way for innovations like passkeys to become the new standard. It's an invisible infrastructure, sure, but it's one we rely on for absolutely everything. Thank you for joining me for this explainer, and hey, keep your eyes peeled for those padlocks.